The human eye processes vast amounts of data simultaneously, capturing entire landscapes in a fraction of a second. The human fingertip, however, operates with a severe bandwidth bottleneck. It absorbs information sequentially, one physical point of contact at a time. Overcoming this physiological constraint required an entirely different approach to reading. It required engineering a rigid, mathematical data structure. The foundational Braille cell acts as a literal binary matrix. It consists of a 2x3 grid, where each of the 6 dots possesses only 2 possible states, raised or flat, 1 or 0. Dictated by the laws of binary combinatorics, 2 possible states across 6 positions yield exactly 2 to the power of 6, or 64, discrete states. By treating the limits of touch as a math problem, this matrix anticipated the principles of digital information architecture over a century before the invention of modern computing. This is the historic institute where Valentin Haüy pioneered early attempts at tactile reading by embossing standard Latin letters onto heavy paper. Mapping visual shapes directly to touch fails the tactile bottleneck. Tracing the intricate curves of standard text is slow, and the physical footprint required makes books impossibly massive. Louis Braille recognized that the solution was to abandon visual representation entirely. He pivoted to binary combinatorics, replacing shapes with codes. This pivot successfully decoupled the underlying data layer from the visual presentation layer. When transmitting information through strict physiological hardware constraints, literal physical translation is inefficient. An algorithmic encoding protocol is the only effective way to achieve high-speed data transmission. Having 64 available states presents a secondary problem: data assignment. If you randomly map letters to those states, the cognitive load required to memorize them is too high. The decade algorithm establishes a base pattern using the top 4 dots to generate characters A to J. Activating dot 3 shifts this pattern to generate K through T. Adding dot 6 shifts it again for U through Z. Because the values follow a predictable hierarchical structure, a user can deduce the meaning of an unfamiliar character by reverse engineering its modifiers. Systematic matrix generation accelerates cognitive pattern recognition. It turns tactile reading from a brute force memory task into a rapid deductive process. The physical medium itself imposes a rigid limitation. To accommodate the specific nerve density of the human fingertip, the distance between dots is strictly standardized to exactly 2.34 millimeters. Writing out verbatim text character for character consumes an enormous amount of physical space, creating an unsustainable footprint for long-form data. Uncontracted Grade 1 Braille requires 13 individual 6-dot cells for the word understanding. Grade 2 Braille acts as lossless data compression. Rather than spelling every letter, it algorithmically collapses high-frequency linguistic clusters, condensing the word into 5 cells: un, der, st, and ing. Recently, the system underwent a major refactoring known as Unified English Braille, or UEB. This update deliberately removed several highly compressed edge cases, such as the single-cell contraction for the suffix ation. Those specific edge cases were creating persistent logic loops and translation errors when processed by modern automated translation software. In modern accessibility engineering, optimal data compression must prioritize deterministic machine parsing rules over maximal spatial efficiency. Visual perception allows for simultaneity, letting the eye parse a 2-dimensional layout at a glance. Tactile processing forces a strict linearity where data must be parsed sequentially. This creates a challenge when encoding inherently 2-dimensional spatial concepts, like algebraic equations or fractions, into a sequential stream. Standard encoding creates ambiguity because the letter A and number 1 share the same physical state, a single raised dot in position 1. The Nemeth Braille code resolves this. Utilizing dropped numbers, the numerical dot pattern shifts downward 1 row within the matrix. Shifting the numerical data downward structurally segregates it from the alphabet, freeing the upper dots to act exclusively as distinct mathematical operators. Forcing complex, multidimensional data through a strict linear bottleneck requires these highly contextual state shifts to avoid data corruption. As digital infrastructure expanded, the original 6-bit analog Braille matrix collided directly with the rise of standard ASCII computing. 64 states are mathematically insufficient to map the 256 distinct states required by standard 8-bit digital operating systems. This Unicode mapping table shows the cell expanding from a 2x3 to a 2x4 matrix. The architecture creates a one-to-one mapping from physical pins directly to digital bits. Dot 1 maps explicitly to bit 0, and the new dot 8 maps to bit 7. The Unicode standard defines only the physical binary pattern of the dots, remaining totally agnostic to the linguistic meaning of the character. Decoupling linguistic meaning from mechanical state allows seamless integration between legacy tactile arrays and modern computer APIs. All of these abstract software protocols ultimately execute in physical hardware. Modern screen readers continuously parse UI automation APIs, demanding high-speed data processing. Translating this digital data stream into a dynamically changing tactile surface requires a precise electromechanical bridge. This cross-section shows the mechanism. Digital 8-bit data flows in, triggering voltage changes across a piezoelectric crystal housed beneath the cell. When voltage is applied, the crystal physically expands, mechanically pushing the pin upward to breach the surface and lock into its binary state. The refreshable display is the realization of the matrix, a dynamic, real-time translation of digital bytes directly into physical terrain. What originated as a 19th-century constraint designed to map 64 analog states has evolved into a global computational standard. The durability of this system is not due to historical sentimentality, but to its rigorous internal logic. By utilizing binary data encoding, the Braille matrix mirrored the exact architecture of the computing machines that would eventually power it. Louis Braille did not merely design an alphabet for the blind. He engineered one of the earliest and most resilient human-computer interface designs in history.